the disturbance created at this end propagates to that end and reflected back, right?
Good morning, teacher.
Today we will continue our lesson on waves. Last time we have studied about transverse and longitudinal waves, right? So Mahalet will demonstrate transverse and longitudinal pulse propagation on a slinky. So we will see that, and next to Mahalet, Gobez and Ache will demonstrate longitudinal and transverse pulse using another slinky made of plastic. Now, the two Mahalets will show us how a longitudinal pulse propagates across the slinky. Once more. Again. The disturbance created at this end propagates to that end and reflected back, right? Have you seen that?
Yes.
Can you repeat it once more? Look, she disturbed it once and stopped. The disturbance propagates to the other end and is reflected back to her hand. Because this has a mass and the reflection and reflection didn't last long. Now you try transverse pulse again. Yeah, the transverse pulse is created at that end, propagates along the slinky, reflected back, and so on. So in general, waves are energy transferring mechanisms in a material medium without actual transport of material itself, right? Of course, electromagnetic waves are exceptions. They don't need material medium for their propagation. Excellent. Very well done. Now, Gobez and Ache will demonstrate the same thing using a lightweight plastic slinky. You want to start with longitudinal or transverse? What kind of wave you want to produce first?
Transverse.
Okay, you start. Okay, that is transverse because the material oscillates perpendicular to the direction of propagation. Next, create a longitudinal pulse. Have you seen the compression moves back and forth across the slinky? Yeah, it's more clear on this red plastic. Can you try it again? Perfect. So, longitudinal wave propagates oscillates in the direction of the propagation. Sound is a typical longitudinal wave. When I am speaking to you, air molecules are vibrating back and forth from my vocal cord up to your ears, right? So today's experiment is on sound wave, its nature and its propagation. And finally, you will measure the speed of sound using a resonance tube. Now, proceed with your experiments. Now, we have seen longitudinal and transverse waves on a slinky, right?
Yes.
Next, I will show you how these two tubes behave when I rotate them. The two tubes are similar in that both are open at both ends. Now, is there any difference between these two tubes?
Yes, it's shape.
Yes, shape-wise. Can you describe the difference in shapes?
Well, that looks more like a track
Whereas this one is a plain tube, smooth from inside. But the inside part of this tube has a circular structure like trachea. It's not smooth from inside. And this tube is filled with air. When I am rotating the tube, the air moves from the lower part out of the upper part. This can be demonstrated by connecting a plastic bag at this end. Now let's see how these two tubes whistle when I rotate them. Have you heard any sound? Only the jiggle of the plastic is heard. Let's do the same with this one. So there is a difference between these two tubes. When they are whistling, rotated, this one can create sound, this one cannot. We will explain this. Look, this one, when this one is rotated, air is running from the lower part of the tube to the upper part, and it is continuously running through the tube. We can demonstrate this by connecting a plastic bag here. Look, here I have an empty plastic bag. I will put this in a plastic bag and fill the bag with air, right? What will happen to the air in the bag when I rotate this? What will happen? The air run out and no whistle. Because this end is closed, the air inside the tube is removed and no continuous flow of air through the tube, and therefore there is no whistle, no sound. So today you will investigate the property and propagation of sound and try to explain why this whistles, why this does not whistle when we rotate. Okay.
Today's experiment seems exciting. I really want to know more about sound. How is sound created?
Sound is created by any vibrating objects. But we have to remember that all vibrating objects cannot produce audible sounds. That is, our ear can sense only those sounds that are in the frequency range from 20 CPS up to 20,000 CPS.
Can you explain what CPS means?
CPS means cycle per second. It's a unit of a quantity called frequency. And frequency, it's the measure of the number of vibrations in 1 second. So, sound frequency, it's the number of vibrations per second of the source.
Look, we can produce sound using this tuning fork, but where is the vibration?
Well, we can't see the vibration because it's too small and too fast. But if I do this, and if I touch the two prongs, that's how the vibration will be stored and no sound will be produced.
That's why we hold it at the handle, not at the prong.
Yes, if we hold or even touch the two prongs, the vibration will be dumped.
You know, it would be really nice if we could see the vibration with our naked eyes.
It is possible. We can see its effect on a ping pong ball. When the tuning fork comes in contact with the ball moves back and forth.
Yes, this clearly demonstrates that the fork is vibrating. It's direct evidence.
Yes, let us try it with another tuning fork. See? Have you noticed the difference?
Yes, there's a difference in sound produced between the two tuning forks, meaning there's a difference in vibration. We clearly saw that on the ping pong ball.
Yes. Each tuning fork has different frequencies, and the frequency is engraved at the handle. On the first tuning fork, it has a frequency of 256 Hertz. Hertz is another unit of measuring frequency. And on the second tuning fork, it has a frequency of 480 Hertz.
Have you ever noticed that when the tuning fork comes in contact with the table, it produces a louder sound? I can show you. We can do it again. Did everybody hear that?
Yes.
Why do you think that is?
I think it increases the frequency of the wave.
If increasing the frequency of the sound, then we would expect a sound of different pitch. Let me show you. This has a 480 Hertz. So when we hit it like this. And this one has 256 Hertz. And when you hit it. So the loudness is the same, but it has a difference of pitch.
This is due to the greater amplitude of vibration of air in contact with the surface. That's why bigger speakers have wider vibrating parts.
Yes, I agree. So this is not due to increase of frequency. It's due to increase in amplitude of the vibration in air.
Can we use different materials other than the ball?
Yes, we can. This is what I saw last time. We can use water, which we can find easily in our surrounding. Can you pass me more water? Thank you. We can easily see the vibration of this tuning fork by putting it in the water. Watch. I'll do it again. You can see that the vibration makes the water splatter everywhere.
Last time we learned about the vibration and how they can occur in different materials. I'll show you. You can look. First, the syringe must be tied with the plastic, and when you hit it, it will turn off the gun. Like this. So this indicates that there's a presence of vibration in here.
This is very exciting. So far today, we have seen that sound is produced due to vibration. But not all vibrations are audible sounds. Only the vibrations ranging from 20 CPS to 20,000 CPS are heard by our ears. And also we can see these vibrations on their effect on the ping pong ball, or water, or even the candle.
Yes.
Now let us discuss how the tube works.
Okay. I think I've got a very good explanation why this whistles and that not. I read it on the internet. Imagine this orange tube is filled with tiny pebbles.
What are pebbles?
Oh, pebbles are smooth, small rounded rocks. So after filling this with tiny pebbles, when we spin it overhead, the pebbles shoot out of the tube. Similarly, it's similar with the molecules of air. When we spin this tube overhead, their molecules comes out of this tube, and as we make the rotation faster, more sound is produced because more molecules of air are passed out of the tube.
But only the corrugated tube sinks, not all plastic sink. Why?
In order for a tube to sink, it has to be corrugated from the inside, having circular shape like this. Because when the molecules of air pass in the tube, they pass from one ridge to another, or one circular shape to another. So when they pass from one ridge to another, they tumble through a vortex. So as they tumble through a vortex, then they will have increased frequency of the sound. Thus produce higher sound.
So far we have seen that sound is produced by vibration, and also that we have also explained the orange colored tube. Now the only thing left to do is measure the speed of sound. So how can we do that?
What do we know about the speed of sound? Is it dependent on the medium of propagation? How much is the magnitude of the speed of sound? And how can we measure the speed of sound in a given medium?
Yes, she's correct. When we want to know about some quantities like speed of sound or speed of light, we need to know some factors affecting it. Knowing of the magnitude of the speed alone is not that useful.
Well, it's not harmful either.
I'm not joking.
Yeah, I know, yes, I understand.
Okay, now so how can we measure sound with materials easily available to us?
Well, a procedure is given, so let us follow it.
So we can use this resonance tube to find the speed of sound. This resonance tube works when the frequency of the tuning fork we're going to use. In this case, we're going to use this tuning fork, and the frequency of air in this column matches. We can make that happen by filling it with water first. We can make this column of water vary by moving this tube up and down like this. So after this, when I hammer this tuning fork and put it here, and she varies the column of water, we find the resonance point, and a louder sound is produced. And in that case, we can find the lambda, the first length. Let's say if we find sound here, that is the length is lambda over 4, and if we find it somewhere around here, that is the second length, it is 3 over 4 lambda. We can find the first resonance point. Listen very carefully. It's louder. The vibration stopped, but as you have observed, it's louder around here. That is the first resonance point, and we can find another resonance point somewhere around here. Most wind instruments use this principle to produce sound.
I think now we can carry on with our experiment. So the first thing to do is set the resonance tube as it is, as you have seen it here. And now somebody practice putting the water level up and down. Okay. And then somebody needs Aksa to do the tuning fork. Okay. So it can produce sound. And Lydia, would you please stand there so you can see where the point of resonance is. Okay, let us start. Okay, we have found the first point of resonance So we can find the wavelength by dividing it with 4. So what's the first point?
It's 18 centimeters.
18 centimeter is our first length.
That is 0.18 meters.
We have obtained our first result, which is 18 centimeter. So in order to get the wavelength or lambda, we must multiply this by 4. And our result is
Our result is 0.72 meter.
okay. Now we repeat this experiment 3 to 4 times in order to get a more accurate answer. Okay, this is around 19 centimeters.
That is 0.17 meter.
Yeah.
And again, we obtain lambda by multiplying this by 4.
0.68.
Okay. Now let us find our second resonance point. It's going to be somewhere around 50, so we don't have to put the water level way up there, and we can start. Okay, our second resonance point is
Around 54 centimeters.
0.54 meter.
and in order to get the wavelength, we must multiply it by 4 over 2, since it's our second resonance point.
$0.72.
Let us try this one more time to be sure. That's around 53 centimeters. Here again, in order to get our wavelength, we must multiply it by 4 over 2.
We obtained 0.76 millisecond.
Now we can measure the speed of sound. Since we know its wavelength and we already know the frequency of the tuning fork, all we have to do is multiply the both.
First we have to find the average
Yes.
wavelength. The average wavelength is 0.72 meter. And the frequency of the tuning fork is?
It's 480 hertz.
So as I said, we multiply both to get the speed. We got the average speed, 335.6 meters per second.
Now we can compare this with the known speed of sound in air, and also calculate our speed of in our temperature, taking temperature into consideration.
Sorry, previously we got 0.72 as our average wavelength and the frequency is 480. So when we multiply both numbers, it should give us 345.6. But I previously said 335, so it should be 345.6.
It's okay, we don't make mistakes. Okay. Now let's compare it with our known speed of sound in air. Speed of sound in air is 331.32 meter per second. For every degree Celsius increase in temperature, there is 0.6 meter per second increase in speed of sound. So around now, our temperature is around, the temperature of the room is around 20 degrees Celsius, meaning there's an increase around 12 to 13 meter per second in the speed of sound. So when we add 331 or 332 to 12 meter per second, we get around 345 and 344. So we have accurately measured the speed of sound.
Yes.
Okay. I think we're done for the day.
It was a very exciting experiment, right?
Yes.